let's talk about force created by current traveling in magnetic field. So we'll call this magnetic electric force, or how about just electromagnetic force? Because why not? Okay, so we learned our right-hand rules about the relationship between a current-carrying wire and the force it experiences when that current-carrying wire is placed in a magnetic field. So what we'll do is we'll start off by laying ourselves out a magnetic field. Okay? X's mean this field, this magnetic field is pointing away from you, like this, pointing away from you. So you're going to use the fingers of your right hand to point away from you. How do we measure the strength of a magnetic field? We haven't covered that yet, but it's measured in terms of Teslas. So magnetic field strength, which is designated as B, is measured in the Tesla. So basically, we're not going to get into the units of what Teslas are measured in. We're just going to understand that they're a unit of magnetic field strength. It's basically derived from the concept of current traveling through a wire creating a magnetic field and measuring the force between another current carrying wire. That's basically where it comes from. It's not super important right now where it comes from. All we really want to do with it is understand how it would work in practice. So let's imagine we look at a hunk of wire, a piece of wire in here, and we imagine that there's a current traveling through this wire designated I. Okay? First of all, let's identify in which direction the force on this wire would be aimed. So take your fingers, point them into the plane of the page, take your thumb, point it in the direction of the current, and your palm should face up. That's the direction that the force is going to act here. So let's call it this. So you're going to get a force like this. Now it turns out that you can actually calculate what this force is based on a few input variables. The input variables that we need to know are force. Well, that's what we're trying to find, and we call it force B. Force due to current in a magnetic field, so it's a magnetic force. I, that's measured in amps, right? L, how long this piece of wire is. That's measured in meters, right? And then its angle to the field. So right now its angle to the field is 90 degrees, okay? So we would write FB equals BIL sine theta. I'll talk about this in a second. All right, so just look in here. Let's just designate what these are, okay? That's magnetic field strength measured in Teslas. There's current in amps. So how much current is traveling through here. And this is the length of the wire inside the field. Okay? The sine theta is interesting. Basically what that is meaning is that if you think of your right-hand rule, the electric character and the magnetic character of these fields are at right angles to each other. So in other words, if I were to take this wire and I were to turn it on its axis around this F such that I could look end on into it, and I could see that the current were traveling towards me in the wire, in this scenario, your fingers and your thumb are pointing in the same direction, and you do not have any force acting in that scenario. So you only get force acting on the percentage or on the fraction of this current that is perpendicular to the magnetic field, right? So this is what this sine theta does. So in this orientation, theta here is 90, and the sine of 90 equals 1. So we just have BIL. But in this case, we have 0 degrees. You're oriented at 0 degrees to the field. You're in the exact same direction as it. The sine of 0 is 0. So in other words, you have no force. And then depending how much it's twisted, right, between this orientation and around to this orientation, right, if we were to spin it, whatever it is off axis, so if it's 0 degrees, 10 degrees, 20 degrees, 30 degrees, 40, 50, 60, 70, 80, 90, you have some fraction of this force happening here. Okay, so how do we use it? It's pretty simple to use. Let's say find FB if B equals 2 Teslas, I equals 2 amps, L equals 2 meters. So a current carrying wire 2 meters long in a 2 Tesla field carrying 2 amps of current, and we are perpendicular to the field. Okay, so FB equals BIL sine theta, so B 2 Teslas, I 2 amps, L 2 meters, and sine 90, which is the same as 1, we're going to get 6 newtons. So 6 newtons of force will act on there. Okay? Let's add a secondary question. What if we were at 45 degrees? Well, what's the sine of 45 degrees? Do you guys know? Also, great point. You got to do your math right. 2 times 2 times 2 is 8, not 6. Sorry about that. Put it right there. So you get 5.6 newtons if you do that. Okay? And that's just how you use that. That is telling you the force acting on a wire carrying a current in a magnetic field. And that's the end of that.